Dear friends, welcome you all for today's discussion. In our previous class, we have discussed about concept of mean temperature of heat addition in Weber power cycle, and we came to know that thermal efficiency of Weber power cycle completely function of the mean temperature. If temperature higher means mean temperature of heat addition is higher, thermal efficiency is higher. But we have seen that there are constraints above which maximum temperature cannot rise above 550 degrees centigrade due to material constraint because so many components of the boiler and all those components which exposed to very high temperature and high pressure steam, these material will have to bear thermal stresses. So due to material constraint, we can't go beyond 550 degrees centigrade. And then next option came to us that we have discussed that if mean temperature cannot be higher than 550 degrees, means maximum temperature, because when temperature increases, mean temperature also increases. And thermal efficiency is a function of mean temperature. But due to material constraints, cost of the material will high if we allow these materials, for example, safety wall of the boiler and piping and insulations and turbine blades, pipe through which steam will flow. All these components, superheaters, all these components will be exposed to very high temperature and thermal stresses will be higher and life of this component will decrease. So that's why maximum temperature for economic and sustainable application of the thermal power plant, we can't go beyond 550 degrees centigrade. And another thing that we can opt for the increasing pressure. If the pressure is increases, higher pressure increases means through which pressure steam will expand to turbine. This pressure increases mean temperature of heatation will also increase. We have seen. But when pressure increases, we have seen that the quality of steam that after expansion through turbine will decrease, and due to moisture content when steam will come out from the turbine and enters into the condenser, due to high moisture content, it will damage the blades of the turbine. So maximum moisture cannot be go beyond 15%. So quality of steam should be not less than 0.85. These are two constraints which fix the maximum pressure and maximum temperature of single stage vapor power cycle. Then what option left for us to further increase the pressure of the turbine? So we will go for the compounding of the turbine. Compounding can be done by reheating. So we will opt reheating. So now today we will discuss how reheating can be used for increasing the pressure, and we can increase the mean temperature of ignition by reheating, and we can also increase the power developed by turbine, because here we will use two turbines, low pressure turbine and high pressure turbines, and then we can further increase the output from the thermal power plant. So let us draw first how we can adopt a reheating method so that we can increase mean temperature of ignition and overall thermal efficiency of the system, overall the thermal efficiency of the thermal power plant, or we can say vapor power cycle can be increased by reheating. So maximum reheating we can go for the 2 reheating, not more than 2 reheating. So let us see how reheating can be achieved and how this system will work. So let us draw first, this is a boiler. So see, this is a schematic presentation of the reheat vapor power cycle. You can see here we have used, instead of one turbine, high pressure turbine and low pressure turbine. This is a boiler, this is a furnace, this is a pump, this one is a pump, and this is a condenser. So how it works? Let us start from the boiler. Steam heat energy supplied from the furnace due to burning of fuel with the air, and combustion product will come out, and heat energy supplied to the boiler, and the water supplied from the pump is coming here, and steam will generate here, and steam is transported to the high pressure turbine first, and from high pressure turbine, instead of passing it to the condenser, first after cooling down the steam, because when steam will cool and pressure will down, we bypass it. This steam bypass it to again in boiler, where in contact with combustion chamber, these low temperature steam heated at the same pressure up to the same maximum temperature, and again supplied to low pressure, because pressure remains constant. So here what pressure is here and what pressure, same pressure will be there. So low pressure, this will be low pressure turbine, high volume will increase because pressure decreases. So this is a size will increase because a large volume will be handled in second low pressure turbine. So remaining steam will pass through low pressure turbine, and then exhaust taking from the low pressure turbine pass it to the condenser, where steam condenses here up to the condenser pressure, and again this condensate will taken by the pump, and this again feed back to the boiler. So this is a working cycle of the reheat cycle. Same thing we can, because this is a process 1 to 2, 1 to 2 and 2 to 3 inside the boiler, and 3 to 4 is a low pressure turbine, and 4 to 5 is a condensation process, and 5 to 6 is a 5 to 6 is a pumping process from the base pump. So we can show this on the TF diagram and HF diagram, so that we can solve this problem, how we can calculate all processes on TF diagram and HF diagram. So see the reduced size, and now we represent this process, reheat cycle process, on HF diagram and TF diagram. So see, this is on TF diagram and HF diagram. Either you can solve it by using TF diagram or HF diagram. This diagram is also known as a Mollier chart. Mollier chart. You see here, I explain here that in process 6 to 1 is a heat addition process, and 1 to 2 there is expansion in the high pressure turbine, and from here it is taken back to the again heating. From 2 to 3 is heated inside the boiler in presence of the combustion gases, and 2 to 3 is heated, and then 3 to 4. 3 to 4 is see again it is expanded in turbine, again expanded into low pressure turbine. So here, due to moisture constraints, we are increasing. This should not be less than 8.5. So moisture presence will increase due to reheating. What is we have increased here pressure P1 is much larger compared to single stage turbine, and again when pressure is dropped to this level, again we use reheating to the same temperature level that we have attained earlier, and after reheating we expanding a low pressure turbine. So we are getting work done in two steps. First step, you can see work done in step 1 to 2 in high pressure turbine, and in 2 to 3 in low pressure turbine. You can find out work done WT equal to H1 minus H2 and plus H3 minus H4. And heat addition Q1 is also in two steps. First step is a 1 to 2, 6 to 1, H1 minus H6, and second step from 2 to 3, H3 minus H2. So these are WT means turbine work we are getting in two steps because two turbines are there, and also Q1 heat addition from 6 to 1, and then from 3 to 4, from 2 to 3. You can see from 2 to 3. 2 to 3 is heat addition process inside the furnace. So from here you can find out WP equal to H6 minus H5. You can also find out H6 minus H5 equal to Vf5 and into P1 minus P2. This is also equal to Vf means specific volume at 0.5 because it is a liquidous state. So specific volume of the liquid at this pressure multiplied by, because pump is doing work, so we are using this, we can also use this equation, pressure difference P1 minus P2. This work is done on the pump, so it is a negative work. From here you can find out pump work and you can find out W net. You can find W net equal to WT minus WP. So these equations you can see here, and all things rest you can calculate by using these equations, because we know that N thermal equal to W net upon Q1. Q1 already we have calculated, W net you can find, this is N thermal, and you can find out steam rate. Steam rate equal to 3600 upon W net. By using this equation, this will be kg per kilowatt hour. kg per kilowatt hour. By using this equation, you can find out steam rate. Means kg kilogram of steam required to generate 1 kilowatt of power per hour. That is a steam rate. All these equations that we have derived for the single stage also applicable for the reheat cycle also. Only thing that is changing here, you can use a higher pressure, much higher compared to single stage, means even 10 times more pressure you can adapt for the reheating cycle, because we are using two turbines. First turbine is a high pressure turbine, second turbine is a low pressure turbine. So this is a big what is the advantage of using reheat cycle? Because we can achieve higher pressure, we can increase the mean temperature we can increase, but maximum temperature remains constant. This temperature we can't increase, but we can increase mean temperature of heat addition by using reheat cycle. All these things that we have discovered here, we will solve one question on reheat cycle that will make your concept very clear. So in next class we will solve some question based on single stage and reheat cycle. Thank you very much for watching my video. Please like and subscribe. Thank you very much and have a nice day.